Now, the basic idea, the thing that we would like to achieve is this. We have been dealing with reference frames also before, different coordinate axes before. So, for example, we were choosing such a coordinate axis, or if you prefer, you could choose such a coordinate axis, x prime and y prime, and given any vector or any position, the position in one coordinate axis, we could write it as Vx in the x hat direction plus Vy in the y hat direction. The components were Vx and Vy. In the other coordinate system, the components were Vx prime in the x prime hat direction and Vy prime in the y hat prime direction. And this Vx prime and Vy prime, they were different than Vx and Vy, although they were referring to the same point. But we know how to relate those two. We had seen that, you can show that Vx prime, Vy prime is nothing but cosine theta, sine theta, Vx and Vy, or minus sine theta, where this is our theta angle. So from one coordinate axis to the other coordinate axis, we have this glossary, this definition of how we can relate the components. The components will be different in different coordinate axes, but we can still relate the two. Now, we had seen on Monday that if you are considering a system, two coordinates that are moving relative to each other, the components of vectors will be different because of length contraction. So if you are talking about, let's say, the displacement vector that a point moves from one point to the other point, let's say, that vector will look different. And not just because of this rotation, but its length will also change. It will have a different length. So that will be the idea. That is what we are trying to achieve. We have on one coordinate axis, let's say, our S system. This is one of our reference frames. And then we have another reference frame. Let's call it S prime. The primed quantities will refer to the S prime system. And we have this point over here. Let's say this is O, this is point O prime. They are moving relative to each other. Let's say that the S prime reference frame is moving with a speed V in this direction, in the X direction, relative to the reference frame S. And then we have this point over here. If you are the observer fixed at O prime, that point will have the coordinates, let's say X prime, at the time T prime, Y prime, Z prime. These will be its coordinates. If you are an observer fixed in the S reference frame at the origin, it will have the coordinates at the time T, X, T, Y, and Z. Well, let me just change the order of it. At the time T, that point will have the coordinate X. In the other reference frame, at the time T prime, it will have the coordinate X prime. Now, this X prime is basically this distance measured in the S prime frame. And this X is this distance measured in the S reference frame. Now, in the S reference frame, let me also call this point, well, I will make these as simplifications. Let's say at the time T equal to 0, I will assume that the origins are at the same point. That will kind of simplify my treatment. And so this distance over here, measured in the S reference frame, is just V times T. Now let me also call this distance measured in the S reference frame as D. So D is this distance measured in the S reference frame. And x prime is this distance measured in the s prime reference frame. So you see, x is simply vt plus d. Now everything here in this expression is measured in the s reference frame. But we want to somehow relate the quantities in the s reference frame with those in the s prime reference frame. So you see, this tells me that we know that length is contracted because there is the Lorentz contraction. We had seen on Monday that x prime, or d, is nothing but square root of 1 minus v squared over c squared x prime. Because x prime is that distance measured in the reference frame in the s prime reference frame. Do you agree? D is what is measured in O. So it will be shorter than the measurement in S prime because of Lorentz contraction. Or, since we had already defined this parameter, which will be important for us, 1 over the square root of 1 minus v squared over c squared as gamma, this is x prime over gamma. This is we know. We had already discussed the length measurement in different reference frames. So we see that x is equal to vt plus d is x prime over gamma, or x prime is equal to gamma x minus vt. So this is one relation between the parameters in one reference. X and t are my parameters in one reference frame. X prime is the coordinate in the other reference frame. Well, we can go to the S prime reference frame. We can consider an observer in the S prime reference frame. So what he will say is X prime is just minus Vt this time, because the S reference frame is moving in the other direction, Vt prime, sorry. Plus x. But x is measured in the other reference frame. He will also observe it to be contracted, so it will be x over gamma. Maybe let me draw it again. Now I'm in the S prime reference frame. I'm looking at considering an observer in the S prime reference frame, so it is moving with the velocity minus v with a speed v in the minus x direction. And I'm writing, this is my x prime. X prime would be just this distance minus this distance. This distance is x measured by an observer that is moving with velocity minus v relative to your reference frame. So it will be Lorentz contracted, so you will measure this distance to be x over gamma. So that's why I have x over gamma. And then the origin has moved by minus Vt prime, according to you. So what remains, x prime, is just this distance, x over gamma minus Vt prime. Or x is equal to gamma x plus x prime plus Vt prime. Well, you see, these two equations are quite symmetric, as they should be. The only difference between these two relationships is the only difference is the sign over here. And that difference is because if S prime reference frame is moving in this direction, the S reference frame is moving in the opposite direction relative to S prime. So the velocity is different in sign. The velocity is different in sign. The speeds are the same. Well, what we would like to do is to relate x prime and t prime to x and t. So what we kind of need to solve these two equations. That is already x prime related to x and t. We have to solve this equation to obtain t prime in terms of x and t. Well, that's kind of easy. Just take that x prime over there, substitute the previous relation. So you get x over gamma is equal to x prime, which is gamma, x minus vt plus vt prime. T prime would be just 1 over v x over gamma minus gamma x plus gamma vt. This is equal to which is equal to, let's say, 1 over v times gamma x 1 over gamma squared minus 1 plus gamma t. Well, 1 over gamma squared is just 1 minus v squared over c squared minus 1 plus gamma t. Ones cancel, so t prime is gamma t minus v over c squared x. So this is my t prime. Let me just collect them. X prime is gamma x minus vt, and t prime is gamma t minus v over c squared x. Well, there is no contraction in the perpendicular direction of the velocity. So y prime is just y, z prime is just z. So these are what we call the Lorentz transformations. You see, in the Galilean relativity case, it's just this gamma factor is 1. And c squared, it's kind of c goes to infinity limit just recovers our Galilean transformations. Because in the Galilean transformations, x prime would be just x minus vt, t prime is just t, and y prime is y, z prime is y. And keep in mind that gamma is equal to 1 over square root of 1 minus v squared over c squared. Either you can consider the limit as c being infinitely large, so then this term is 0, so gamma just becomes 1, and this term is also 0, so you have the t prime is equal to t. Or you can say that speed is very slow compared to the speed of light, and again, gamma is 1, t prime is t, x prime is equal to x minus vt. So in a sense, this tells me that the Galilean transformation is just an approximation to the Lorentz transformation in the case when the speed of the object is slow compared to the speed of light. The speed of the reference frames relative to each other. You see, whenever you are talking about speed or velocity, you have to always specify a reference frame. So the question, can we move close to the speed of light? Doesn't really make sense. Because we are moving close to the speed of light relative to some observer. Most of the time what we mean by saying that can we move close to the speed of light is, can we accelerate an object that moves close to the speed of light relative to us? We can. And we are constantly doing it in accelerators, for example. The protons in LHC, for example, they are moving at a speed which is 99.89% the speed of light. They start from rest, almost rest. But they are small objects. Do you remember the definition of an event? What do we call an event? Okay, we made this definition in your first year. An event is basically a position and a time. So that is what we call an event. An event happens at a given point at a given time. Then you can talk about the separation, the distance between two events, the time between two events, etc. So, in a sense, these are also our transformations for the coordinates and time of events. Now let's derive our previous relations. So, for example, these relations already incorporate in the Lorentz transformations already tell us about the Lorentz contraction. So in the Lorentz contraction, what we do is we measure the position of 2 points at the same time. So there are 2 events there. We first, the beginning of the object at a given time, and the end point of the object at the same time. So there are these 2 events, at least in one reference frame, their position is measured at the same time. Delta x prime, that is the separation between those 2. Delta x prime, let me just write first this. In this form, this is delta x minus v delta t. Since I'm measuring length, I have to be measuring them at the same time. So delta t is 0. Delta x prime is gamma delta x. Or delta x is equal to 1 over gamma delta x prime. This is our result for Lorentz contraction. That is how we define the length. You see, if this object is moving, you measure its endpoint at one time and the beginning point at some other time, the difference between those 2 points is not equal to the length, because during that time it moved. You have to measure the starting point and the end point at the same time and measure the separation between those 2 points. That is what we call the length. So that is why I take delta t is equal to 0. Yeah, Lorentz contraction. Yeah, we derive the Lorentz transformation using Lorentz contraction, so it's not a surprise that it is already incorporated in the Lorentz transformations. Now, you tell me, what are we trying to measure? What are we trying to compare? So this is our system. So we have, let's say we have an object that is at rest in the S prime reference system. Okay? So in which reference frame are we measuring its length? In the S prime system or in the S system? Now you see, it has a length in the S prime system, which we call it delta X prime. Okay, this is delta X prime. And I'm interested in the length of the object in the S system. So I'm trying to figure out the length of the same object in the S system. So in the S system, I have to measure the starting point and the end point at the same time. That is delta T. So I have to make those two measurements, those two events, they have to happen at the same time in the reference frame in which I'm making the measurement. And in that case, we had found that delta X is equal to 1 over gamma delta X prime. Of course, these two measurements that are at the same time in the S reference frame, for an observer in the S prime reference frame, he will say that, no, I'm not measuring them at the same time. Because simultaneity is itself a frame-dependent quantity. When I say that delta T is equal to 0, that means that I'm measuring the position of the two ends of my object at the same time in the S reference frame. But two events that happen at the same time in one reference frame do not happen at the same time in a different reference frame.
So if the object is accelerating, these are not relevant.
Acceleration, we are not taking them into account. You see, the relativity at this point is the relativity of the velocities. Acceleration are still, in a sense, absolute. If an object has an acceleration in one reference frame, then, if an object is accelerating, if a reference frame is accelerating within this framework, let's say, we can tell whether our reference frame is accelerating or not. In that sense, it's not relative. We cannot tell whether a reference frame is moving at a constant speed or not. So that's what we call relativity. But we can still tell that whether a reference frame is accelerating or not. Now the next step would be to claim that whatever you do, you cannot tell whether a reference frame is accelerating or not. So that would be the next step. And when Einstein did take that step, he discovered general theory of relativity. So in the general theory of relativity, it says that if you are in a closed room, you cannot even tell whether your reference frame fixed in your room is accelerating or not. Sufficiently small closed room. And there the idea was acceleration is basically the same thing as gravity. So you cannot tell whether you are gravitating or accelerating. You cannot distinguish the two. So that's why we say that you cannot tell whether you are accelerating or not. You might be either accelerating or you are in a gravitational field. But that's kind of beyond our perspective now.
Ama hocam asansördeyken mesela asansör yukarı çıktığı zaman yani ivmelendiğimizi hissedebiliyoruz.
No. If you think that the elevator is closed without any way of looking out, you don't know whether you are accelerating or whether there was some other black hole that came close to the elevator. Of course, when you open the door of the elevator, you will know, but not while you are inside the elevator. How? No, well, you see, what you are feeling is you are feeling a larger force. That's the only thing you are feeling, right? Which can be either due to the acceleration or due to, for some reason, the gravitational field at the position of the elevator has increased. For some reason. Maybe while you are inside the elevator, a black hole, as I said, just came very close to the elevator. What is that? That's what I'm saying. You are feeling an additional force. Exactly. But what I am claiming is that what you are feeling is not necessarily due to acceleration. But of course, in our everyday life, we never saw a black hole come close to the elevator or the plane. So you know that the gravitational force will not be changing in your position. So any change in your force will be due to your acceleration relative to your initial reference frame. But that's an assumption. That is, okay, that's a intuition, let's say, based on our observation, previous observations. But the laws of nature doesn't really care about your intuition. In principle, the other cases should also be possible. And in that case, you cannot really be sure that there is no there is acceleration. Anyway, as I said, that is beyond our scope for this course, so let's go back to our special theory of relativity.
Hocam şimdi biz yapıyorduk mesela modern fizikte. Roket var işte, pist var, pistin üstünde bir gözlemci, roketin içinde birisi var işte. Birbirinin boylarının kısalmasını falan ölçüyorlardı. Mesela orada Lorentz transformation kullanabilir miyiz? Yoksa
sure.
Ayrı ayrı her birinin ölçülerini mi karşılaştırmamız gerekiyor?
You see, what do you mean by measurement? So you are basically, for example, if you are measuring the length, you have to make two measurements corresponding to each end. You have to specify the position. So that is two events. Then just use Lorentz transformation to compare the coordinates of those events, coordinates and times. That is basically what I did over here. You see, here what I did was, you see, x prime is gamma x minus vt. So let's say I measure the endpoint, x prime, the endpoint at the time t1, and I found out that it was just xe at the time t1. And then I measure the final point. This was gamma xf minus v at the same time t1. So in the S reference frame, there are two events that happen at the same time, and one happens at xe, the other one happens at xf. So these are two measurements, the position of two measurements that are made at the same time in the S reference frame. Then it's no longer a length measurement. Because length measurement, by definition, it has to be at the same time. Sure, you see, each length measurement has two events. And these two events has to be at the same time, if I want to call it a length measurement.
Hocam ben aynı anda hem başını hem sonunu nasıl görebileceğim ki?
You have to devise your setup in such a way.
Ama mesela cetvelde de dahi ilk önce bir buraya bakıyorum, sonra buraya bakıyorum. Bir zaman farkı oluyor.
Let's see. At every point, put a detector at every point. And you agree that they will all measure whether there is an object right across them or not at the same time. You synchronize them. In a single reference frame, there's no problem with synchronization. So they all measure whether, at every point you put a detector, they all make the measurement at the same time, and at that time they see whether there is this object right across them or not. As it's moving at a given time, they make the measurements, and this one over here will say, yes, there is something right across me. Next one will say, no, there is nothing. So you know its position, the position of this object at that time of the measurement. So all the detectors here will say yes, 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 yes at the same time, and the detector over here will say yes, but the next one will say no. So all these detectors will measure the position of this pen at the same time. You don't need to have a look yourself. Let's look at one thing. Let me calculate this one. Why I calculate that one will be apparent in a moment. Well, this is equal to x prime is gamma x minus vt squared minus c squared t prime is gamma t minus v over c squared x squared. This is equal to, well, all of them has a factor gamma, so this is gamma squared x squared minus v squared t squared plus v squared 2t squared minus twice x vt. This is the first term. Well, the second term will be minus c squared t squared minus or plus v squared over c to the 4x squared minus twice v over c squared xt. I just opened up the parentheses. Well, let's see. Here I have minus 2x vt. Here I have minus 2vxt divided by c squared multiplied with minus c squared. So if I just cancel the c squares and this minus makes plus, I end up having twice vxt. So it just cancels that twice xvt. So these are canceled. Now let's see what remains. This is gamma squared x squared 1 minus v squared over c squared minus c squared t squared 1 minus v squared over c squared. But keep in mind, gamma squared is nothing but 1 over 1 minus v squared over c squared. So these will just cancel. So x prime squared minus c squared t prime squared is x squared minus c squared t squared. So it doesn't change. You see, if I go from one coordinate axis to the other coordinate axis, one reference frame to the other reference frame, the events will have different times and different positions, but nevertheless, this combination will not change. So let's say we define this quantity c squared t squared minus c squared t squared plus x squared. Well, let me also add the plus y squared plus z squared because they don't change anyway. This is what we call an interval. That is invariant under Lorentz transformations.
Ne arada?
We will see. Well, most of the time it can be also written to say that it's an interval. Maybe this way of writing it is more useful. Let's say delta this is what we call the interval. So basically, what is this interval? We will study it in some detail, but let's just consider two events. The events happen at a given point at a given time, each one. So in a given reference frame, they are separated by some distance, and they will be separated by some time, these two events. Now, of course, their physical the space-like separation and their time separation will be different in different reference frames. Different observers will see different things. But nevertheless, they will all agree that this combination is a given number. Well, if you go back to our rotations in 2 dimensions, the example that we had looked before, you see, rotations, they kind of conserve certain quantities, like the length of the objects. They do not change under rotations. Or the angle between two objects, they do not change under rotation. Basically, we define a scalar product that doesn't change under rotation. The length can be written in terms of a scalar product, or the angle can be written in terms of a scalar product. So those things, a scalar product is not changed under rotations. Now, of course, if you just go from one reference frame to another reference frame that is moving, certain length, in the Galilean relativity case, these three things on their own do not change. This thing doesn't change on their own, so this combination doesn't change anyway for Galilean relativity, let's say. But in Einstein theory, there is length contraction. So if you go from one reference frame to the other reference frame, this combination, which is the length of our vector, does change. But this also changes. So they change in such a way that this combination doesn't change. So that is the nice thing about this combination.
Hocam şimdi iki tane nokta. Işık hızına yakın bir hızla böyle döndürülürse aradaki açı da değişmez mi?
We will see. We will come. Different observers will measure the angles differently, geometrical angles. We will see how they change. And to calculate that, the invariance of this quantity will be important for us. So we will just basically use the invariance of this thing to calculate how the angles change. Now let me also just note one more thing before you go for a break. So you see, these are our coordinate transformations. Well, I can basically write it in this form. T prime, x prime, y prime, z prime is equal to t, x, y, and z. Or let me just put the c also over there. If I put the c over there, it will look easier, and I have the same units everywhere. CT will have the same unit, X prime, CT prime will have the same unit as X prime, Y prime, and Z prime. That's why I put the CT over there. So CT prime will be just gamma times CT minus V over C. So here I have V over C times CT. Well, you see, the velocity, if I just call this combination a unit, the velocity doesn't really appear at all on its own. It's always velocity, the speed over the speed of light. So that thing I will call V over C. This is my definition. So in terms of this thing, gamma is just 1 over square root of 1 minus beta squared. So then, in terms of these newly defined quantities, this matrix appearing over there is just gamma minus beta gamma 0, 0. X prime is minus beta gamma CT times gamma plus gamma X 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's 4 by 4. Let's see. Well, let's look at our geometrical rotations in that two-dimensional space. We say that basically we call it a two-dimensional space, mainly because if you just consider a coordinate rotation, those two components, they just mix with each other. Well, we have exactly the same thing over here. If you just go from one reference frame to the other reference frame, X, Y, Z coordinates and the time, they just mix together through this matrix. So in that sense, we call the time our fourth coordinate. It mixes with the other ones. It doesn't behave independent of the other ones. In Galilean relativity, time was independent of the coordinates. So that's why in Galilean relativity, it's not really a fourth coordinate. But now here, everything just gets mixed up. So you cannot really separate any one coordinate from the other ones. And most of the time, just for notational convenience, I mean, we don't write these matrices all the time. We use what's called index notation. You see, for V, the V vector, I can also denote it by its components VI. I just have a similar notation for these four vectors. So I call X the position and time, X mu. This is equal to CT, X, Y, and Z. X0, what I call CT, X1 is X, X2 is Y, X3 is Z. So that transformation, Lorentz transformation, I can write it as X mu prime is, now I have this matrix lambda. This is what I call the matrix lambda. I take the mu and nu index of multiplied with X nu. Nu. Mu and nu. And this mu and nu, they can take the value 0, 1, 2, and 3. And you see here I have a summation over nu, summed over nu from 0, 1, 2, 3. although I don't write it explicitly. This will be the notation we will be using. And just like anything, under rotation behaves like the coordinate vector at the top part of the screen is something we call a vector. Now here, anything that transforms like this from one reference frame to the other reference frame in this form is what we call a 4 vector, meaning that it's a vector with 4 components. No, it's a vector. It has a single index. And in fact, rotations can also be written in this form. For a rotation, lambda is just, let's say, the time coordinate doesn't change under rotation. Let's say x and the y components gets mixed up. So we are rotation around the z-axis. This will be cosine theta, minus sine theta, or plus sine theta, sorry, this is plus. 1, the rest are 0. This is our rotation. So 4 vectors, at least the 3 part of it, are just ordinary vectors, should be ordinary vectors.
Hocam peki T'nin direction methodu nasıl bir şey?
Yeah, we will discuss. You see, when you talk about direction, you most of the time mean the direction in 3-dimensional space. So asking what is the direction of the T vector in the 3-dimensional space sense doesn't make any sense, doesn't have a meaning. But we will draw some space-time diagrams, the world line, etc., where we will have a direction for the time.
In previous matrix, so if velocity is much less than speed of light, so beta will be 0 and the matrix will be an identity.
Sure.
So nothing will change?
Nothing changes.
But velocity is very low with respect to speed of light. The important thing is its ratio to the speed of light or its magnitude.
Well, you see, one thing you have to be a bit careful about if the velocity is close to the speed, is much smaller than the speed of light. When you are making out this multiplication, for example, this term over here gets multiplied by c. So when v over c goes to 0, beta times c just stays v. So it doesn't really become 1. So setting the limit, just setting beta to 0 is not really correct because it is multiplied by c. So beta is small, you are right, but beta times c is not small. So you cannot set it to 0. Since you are not allowed to set it to 0, this beta just remains over there. Close to the speed of light, this beta will remain, this will remain, so you have this. No, this will probably go to 0 because it's not multiplied by c. But this beta will stay, it's multiplied by c. If you want to get if you want to recover the Galilean relativity, you have to keep this one. This one, these are just becomes 1, you still keep this one, and so it doesn't become the identity matrix. You recover Galilean relativity. Only if v is exactly equal to 0, then this becomes 1, but that is what it should. If v is 0, nothing is moving. So the coordinates in one reference frame is the same as the coordinates in the other reference frame because both reference frames are the same.
Şimdi şurada y için bir var ya.
Okay. Of course, this is the Lorentz transformation matrix for a velocity in the x direction. If the velocity is not in the x direction, in some other direction, lambda will be different. It won't be this lambda. Let's give a 10-minute break and then we will continue.